All right, hello and welcome everyone to GLOBEBUSTERS Season 14, Episode 15. I'm joined today by Shane G, Stone G, and Van B G from Ether Cause, who recently did a presentation on terrestrial refraction and the boundary interface, which is the mechanism that is required for an image to be projected into a new medium and then be lifted up or refracted down, etc., but preserving its shape and image. There has to be a boundary interface. So Vanby brought that to the forefront there. And today is going to be doing a follow-up on terrestrial refraction and just going deeper on what he already laid the foundation for. So
Nice.
Vanby, whenever you're ready, my good sir, take it away.
Sounds good. So yeah, first off, thanks for having me. This is fun, and I think you guys foster Aether Cause particularly fosters a good environment for researching and presenting. I think that's presenting ideas is a pretty solid way to further your understanding. And so thank you for giving me that opportunity. I appreciate it. I'm excited. I really like this topic of terrestrial refraction and just refraction in general, because everything we see is refracted light. Our eyes refract the light and form images by doing so. And air refracts light, water refracts light. It's a huge part of our everyday life. And it's also integral to the conversation when discussing if we live on a sphere or not. And so what we're going to be doing today is examining the claim of refraction. And I like this is an image here of the Chicago city skyline. And I think this is a poster child for this phenomenon we are told that is happening. Because we live on a ball, the distance away over Lake Michigan of these buildings is geometrically impossible to be viewing these buildings. And so what they say is, the claim is refraction is lifting these images up, and so we can see them. And this phenomena, or this observation, is especially the Chicago city skyline, is extremely common. And there's many professional photographs of this, these beautiful ones I'm showing you guys. And there's also just people standing at the beach, 50, 60 miles away, and they can see this thing. And so yeah, this is the claim. And as you can see, they're right at the shore, and they can see these buildings directly. And so we're examining that claim. Can this happen? Can this effect that they claim actually be happening within the single medium of air? And this is a pretty one of my favorites. It's like a mini Mount Canigou. It's got the sun behind it. Here's a couple just quick videos, just kind of highlighting. The audio is actually not even important, but highlighting that this is a very common phenomenon that normal people see all the time. This video is kind of cool because it's a time lapse, and it's going to go just for a couple seconds. And as it goes into the nighttime, you will start to see a sort of miraging effect happening, increasing as the night goes on. That's a cool image there.
Look at the amount of Earth curve change so rapidly. That's crazy how the physical elevation caused by that horizon keeps wobbling like that. That's amazing.
Yeah. So I just wanted to kind of really break down this claim. And this is, a lot of us have probably heard this before, but just for people coming into the conversation of refraction, if you just Google, if I'm standing at the ocean shore and I'm 6 feet and I'm looking out at my horizon, it'll tell you that the geometric horizon of the Earth is 3 miles away from you. So this is the limit of our geometrical vision if we're standing at the shore looking over water out at the horizon. And then it'll tell you that this is neglecting atmospheric refraction. So that's the claim of why we can see further. But yeah, geometrically, we can only see 3 miles away standing at the shore. And this is because of the Earth curvature formula. And I'm just going to breeze over this. So the common formula for Earth curvature is 8 inches per mile squared. And that is an approximation. And so sometimes people will say, using this equation is false. You need to use the real equation. But in reality, when you ask Google to do the math for you, it'll tell you that up to 100 miles, an observation of 100 miles, it's perfectly fitting. The 8 inches mile squared formula is perfectly fitting the spherical geometric formula. So it's just a simplified formula that we use. I know I've heard some people say that, you're not using the right formula or whatever, but it's an approximation, so it works perfectly fine.
So for the people, for the benefit of the people on their phones and tiny screen world out there, is there any way that you could zoom these in, take up more of the screen? Yeah, that's vastly superior. Now people can see what you're talking about.
Yeah, I'll remember.
Good stuff.
Thank you. Sorry about that. Yeah,
he's doing a presentation for ants.
I'm learning as I go here. But yeah, this is just okay. So we're going to look at
learning.
We're going to look at a diagram of just breaking this down further, just so everyone understands the claim. And so on the left here, we have the observer, the little blue arrow, and on the right, we have the Chicago skyline, and then the dotted line is the horizon, the geometric horizon of that observer. So right in the middle here, you see he can't see anything further past this horizon, and the skyline is physically blocked. And so the claim is, this is very crude, not to scale, obviously, but I drew the green arrow there, and that is what they're claiming is happening, is that this image is just directly being lifted straight up so we can see it within our line of sight. They're claiming that the light from the object is bending into our vision, and it's making us see this effect. And so that's what we're examining, is can an obstructed object refract within a single medium and cause this effect? And I threw this slide in here because this is what they also claim. This is, we're talking about objects on Earth, but also when you look at the sun, we're spinning. We're claimed to be a ball on a sphere spinning, and so the sun has a true position that must be traveling if the Earth is spinning. So when we see the sun, sometimes we see the sun at the horizon not go down. It lingers on our horizon, and so that what they have to say is that the true position is below our horizon, and that refraction is lifting it up. Because if we were on a ball, it has a true position which is below our geometric horizon. So that's just quickly going over that. This is to further highlight that this phenomenon is very very common, and this is taken from a news article in Barron County, Michigan, that did the kind of a famous report on this phenomenon. And they claim they talked to the guy who did the picture, Joshua Nowicki. He took it 60 miles away, and they clearly state under normal conditions that the Chicago city skyline should not be visible due to the curvature of the Earth. So this is just highlighting that this has been reported on, and then and this is the actual image that he took. This is kind of a popular image of that. And so when you can look up Earth curve calculators, and again, we're just breezing over the basics here. If you plug in, and this is just to confirm that over 50 miles, if you're a 6-foot observer, and a 6-foot observer looking out at the horizon over 50 miles, there should be over 1,400 feet of curvature. And the same thing with 60 miles, there's over 2,000 feet of curvature. So you can look up these curvature calculators. You can plug in the numbers, and it'll tell you how much curvature how much visible height is hidden. So we're establishing that clearly this Chicago city skyline is hidden geometrically. And then you can also look up the tallest building in Chicago only stands 1,400 feet tall. So clearly the building should be invisible. And so this next video I'd like to play. Oh, I might need to reopen this this window if I can do that really fast, because it does this sometimes where the. Can you give me just 1 second? Let me reopen this.
Nope,
sure,
has to
It's
be
your show.
flawless or whatever.
Yeah, right now. I need it.
Okay, 1 sec. Boom.
While you're doing that, though, you gave a figure for Willis Towers elevation, altitude rather, its height, and I'm curious if you took the time to take a look at the buildings directly adjacent and what their heights are, and do a kind of proportional extrapolation to how much of the building of Willis Tower we can actually see out of its total height. Did you do that? Because I find that's always an interesting outcome.
Yeah, I think that is really interesting. I did not do that. I'm more just trying to speak on the general observation, and I think there's a lot to glean from what you just said for sure. You know, the way our perspective maps those objects into our, informs an image for us, and how,
Oh, totally. It's that we're seeing this figure of 1,450 feet right here, and it comes down to the claim that we're making that the building shouldn't be visible at all by 300 feet or whatever it is. But the point is, how much below that 1,700 feet that we shouldn't see are we actually seeing? You know what I mean? That if we know that it's 1,450 feet and we're seeing roughly, say, 9/16 of the building, then you take a direct subtraction from the total you shouldn't be able to see. And that just, drives globies crazy.
Right. Yeah, maybe in the next presentation I can work that out. But yeah, for sure. But okay, so this is a video from that news organization, and
Is there supposed to be audio with it?
there is, and if it's not working, that's totally fine. So what's happening here is they've taped a picture of the Chicago city skyline to the wall, and they have an obstruction here, and they have him put at it. This is the observer. This is his sight line, and you cannot and they have a lens here that they move in and out of the sight line, and so when he's looking out at his horizon here over this obstruction, he can't see the picture of the Chicago city skyline, and then they move in the lens, and then he can see it. And what this guy here, this refraction scientist or whatever he is, he said he's saying that this is simulating a thermal gradient, and that's where I completely disagree. But we'll get into that in just a little bit. But so what they're doing is they're using a lens to refract the image around the obstruction, and they're claiming that's the same effect as a thermal gradient or a density gradient, which I totally disagree with. But yeah, so so that's the claim, that refraction is bending this city skyline around the curve. And so what I postulate, and based on the demonstrations we're going to go over, our understanding of refraction and how it's measured, and then also geometric optics, I think this is a line of sight phenomena. What you're seeing here is actually the city, and according to what we know and what I postulate, it has to be within the line of sight. So
can you zoom in on it too, please?
Yeah, sorry. Remember that.
For me, the clincher is clarity. That people forget that refraction is not something that helps you see things more clearly. Refraction is a form of visual distortion. Heat-related lapse, like you said, thermal gradient related, a lapse rate related phenomenon. And because we are looking at individual lights on the building, clearly, sharply defined rectangles, that tells us that it's an original and not a mirage. You know what I mean?
Yep. And
we're not seeing it better because of distortion. And if it was distortion, it wouldn't look anywhere near this clear. So that's how we know we're looking directly at it.
Mm-hmm. Yeah. We will go over examples that show that exactly what you're saying. The blurring and the stretching. It's not a clear image. And like in some of those pictures I showed originally, the nice the high level photography ones, like you're getting extremely crisp lines. And this is a little pixelated here, but yeah, it's very clear. You can see detail, and yeah. So just the most basic definition of refraction is the bending of light as it passes through different media. And terrestrial refraction is the gradual bending of light rays as they travel horizontally through the Earth's atmosphere due to gradual variations in air density and refractive index caused by temperature, pressure, and humidity. So terrestrial refraction is referring to refraction within a single medium, one medium, and that's why it has a gradual variations, and that's what defines a single medium, and we'll get into that a little bit more. I wanted to briefly go over just the equation for terrestrial refraction, because I finally went down and went through it a little bit, and it's kind of funny to me what's going on in this equation. But let me pull up my notes real quick. But yeah, so firstly, this equation, we have K, which is the coefficient of, it's a ratio of the radius of the Earth, which is big R, and this is the assumed path curvature of light the rays will take, that they have to take to fit the spherical formula. So it ultimately, what this is a curvature correction formula. It's telling you how much curve you aren't seeing.
So what is the unit of measurement for small r?
Small r would be, I'm not sure.
That's a really small r.
What I learned about r is it's the assumed, not measured, not directly measured. It's the assumed rate of curvature of the light path must take in ratio to the radius of the Earth. And
okay, so it's one radius over another then, as far as
right, exactly.
Okay, fair
exactly. Enough. And I have to zoom into these. So when you look at how K is derived, N is the refraction coefficient, and that's going to be of air. And so they use the height, and so they have a ratio of the refractive index in the height, the height of the atmosphere, okay? And then they sneak in the radius of the Earth here. And so that, to me, what they're doing is they're wrapping that, we actually measured this, the N. This is the density gradient we've actually measured, and then they're wrapping it around a ball with this coefficient. And so to me, that's like they're sneaking that in. That's assumed because the radius was the curvature isn't measured. They're just throwing it in. And let's see here. So this just defines the terms here. K is the dimensionless ratio expressing how much curvature the light path has relative to the Earth curvature, and the rate R, the radius of the curvature of light path. So to make this useful, this K value, what they can do is they can spit out a effective Earth radius formula. So what's happening here is we're taking the radius of the Earth and we're dividing it by this K value, and we're getting an effective radius of the Earth. And what this is doing is it's making the radius bigger. And so it's essentially making the Earth flatter. So when you see something, and so that's why it's a correction formula. It's spitting out what curvature is missing by extending that radius. So average air conditions, K, is known to be 0.13 to 0.17. This is the value they use. And when you actually do the math, it's simple. Take the radius of the Earth and you divide it by 1 minus K. 1 minus that value. And so this is the new radius of the Earth you would get. So it's essentially just flattening out it's correcting for that curvature. It's increasing the radius, making it flattening out the Earth, basically.
And currently you're showing 15% increase.
Am I? Yes, exactly.
Yeah, I just threw one over the other then.
Right. Okay, so I want to get into demonstrate that. That's just going over the formula. I thought that was interesting. It feels like it's full of assumptions. It's not really meaningful in the discussion because it's so just, the K values aren't even measured. They're assumed from the index of air is measured, but they're not on the day of the observation. They're not measuring the refractive values of the air in between the observations. And the path of the light, that's assumed. They're not directly measuring the path of the light. So it's all just throwing in the radius, and it feels all assumptive to me. So that's what I'll say about the refraction. The terrestrial
and circular.
Yeah, very very circular.
Right, circular. Yeah.
It's very curve fitting.
Yeah, you can't talk about refraction without them saying, well, actually, we know the specific rate at which it's bending because we know the rate of the radius of the Earth. So I can help you with that refraction coefficient. And that's what it's always been. Exactly,
yeah. Okay, so we're getting to some demonstrations now. And I used this one in the last presentation, but I like this one. This is from Jesse Path of Light, our good buddy. And I just like it because he did a nice setup here. And so what you're looking out a window. This is a camera, and he put an obstruction, the dark, curved, opaque, this obstruction down here at the bottom of the image, and he's blocking a house which is just across the street. So normally we would have sightline to the house. He's blocking it with this obstruction, and then he's placing a prism just on top, and it is refracting the image around the obstruction. And this is to show that, look, refraction can bend images around the curve of the Earth. But the problem with this is this effect is not, it's not equal. Refractive effects are not equal. Like, there's different refractive effects. And this one is specifically happening because of the second medium he's placing in there, which is the prism. And so going back to the reporter who was sliding the lens in front of the picture of Chicago skyline and causing the refraction, the same thing is happening in this. This is the same exact effect. So we're going to talk about real fast this is image formation at the boundary interface, at the boundary between the prism and air. So there's a quick little diagram here, and this is kind of just to get to understand where this is happening. So at the top left, we have an object which is emitting light, and we're representing this with a ray here. And the top medium 1 is, we can call it air, and medium 2, we can call this the prism, just like we were looking at. So when it hits this boundary, it abruptly changes refractive indices, because there's a different refractive index between air and the prism. So it sharply bends, and we can see the image formation happen at this boundary. And this is a known effect. And this effect does not happen in a single medium. You need the two mediums for this effect. So it's completely unanalogous to what we're seeing when we're looking over long distances over the ocean. This is a completely different effect. And I think this demonstration here highlights it really well. And so we're looking at a sink, and we can see the lip of the basin, but we cannot see the drain. But when we fill it up with water, the drain reveals itself. And this is that boundary interface. The light comes from the drain. It's in the index of water, and then it hits the boundary interface, which is where the water meets the air, and then that hits a different refractive index, so it bends abruptly. The image is formed, and now we can see the drain behind the basin. And then I like to take this one step further and say, just to highlight, that if you were to continue filling up the bathroom from floor to ceiling with tap water, and the observer and everything was immersed in this room of water, you would no longer see that effect. And this is because of, I want to define the different medium types here. We have homogeneous mediums and inhomogeneous mediums. So when we're looking in air, we're in a bathroom, there's no temperature density gradients in the air in your bathroom, and you're at such a short distance, it's considered to be homogeneous. So it's uniform at each point. So light travels straight within homogeneous mediums. And within inhomogeneous mediums, that the light, it's not uniform. So there's a density gradient, and so it will travel smoothly with the density gradient. So what's happening here is, this is highlighting that specifically the boundary interface is creating this image of the drain here. And when you go back, if you were to fill the room with the homogeneous medium, the light rays only are traveling straight, and so this effect wouldn't happen anymore. So yeah, this is just highlighting that this is a specific effect of refraction. This is not within a single medium. This requires a secondary medium for this effect. And that's why it's unanalogous to reality. So quick diagram, just to kind of hit this home, is this is the paths of light traveling within a density gradient. And as you can see, there's, unlike that other diagram where it's sharply changed at the boundary layer, here it is gradually, the rays of light represented here in the red lines, they are gradually bending toward the denser part of the medium, which is the darker blue. And so this is how light is described to be traveling within single inhomogeneous mediums. And so now I want to go over a few examples of in the lab experiments, and these are all taken from, like, if you just search up common, there's a whole bunch of them of people replicating these phenomenon, these refractive phenomenon in the lab, and in all these examples I'm going to show, it's all with a single line of sight, and they are all manipulating specific variables to create these effects. So we can recreate these simply in the lab with line of sight. What they aren't doing in these experiments, what you won't see, is them bending these effects around obstacles or obstructions. So we can understand these completely through in the lab experiments, with a line of sight to these unobstructed images. So this first image here, we're looking at a card that has the words Fata Morgana written on it, and we're looking through a density gradient. And as the camera observer changes its height and distance away from this image, we can create these effects through the density gradient. But within the lab, they're not obstructing it. They're observing this completely with line of sight. So this is with the density gradient, we can observe this effect. This effect here is with turbulence. So they are looking through, they have this card in a tank of water, and they are stirring up the water, and they're showing that turbulence can cause can enhance refractive effects. And then this one was kind of from an older paper. Sorry, I actually forgot to link these papers, but they're really common. They're easily searchable online, searching up mirages in the lab and stuff like that. And so this guy set up a hot plate, and so this is a thermal gradient, and this is showing that when he changes his relationship of height to the plane of the hot plate, these effects happen. So I think up top here he's a little higher, and then he's going, as he's lowering his camera, he's seeing these effects change. This is showing that the thermal gradient and our relationship between, viewing through that thermal gradient, our height can cause these types of effects as well. So oh, there's one more I wanted to show, and this one was kind of interesting. What they did was they set up a hot plate, and then they put this this pot on top with ice in it or something. They made it really cold. I think it was ice, and so they created a sharp density gradient. They had the hot plate with the cold surface right above it, creating a sharp density gradient. And so first they shot a laser through it, and they measured that the laser was bending, and then they stuck a camera through that little opening, and they observed this refractive effect. And this is kind of a miraging and a blurring. So you can see on the left, this was before the gradient was turned on, and this was after on the right. And so there obviously is there's a bending of the image going on. But what the problem is that they attribute this effect to being the fact that the height of their heads has gone down a little bit. They're attributing that to being possible bending around an obstruction. And what I'm claiming is this effect has to be still within the line of sight. You still need line of sight to the object to be able to see the effect. And this is how they're done in the experiment. They're not obstructing anything. They're showing the bending. So I think that's a common misconception, is that because images can bend, that they can bend around an obstruction. So yeah, but again, this is just showing these effects are all done in the lab with line of sight to these unobstructed to these images, and they're creating these effects. Briefly, I wanted to talk about lasers just really quickly, and because lasers is kind of a common argument used of why we can, a really basic argument of why people think we can see images around an obstruction. You know, they shoot a laser through a tank which has a gradient, like a salt gradient or a sugar gradient, and we see the laser bend. And so they're like, oh, bam, light bends around the ball. That works out. But to me, this is extremely unanalogous to how we see in reality. First off, this isn't explaining anything about image formation. This isn't seeing an image. This is viewing a laser. And what I think the important part about this is the coherency of the light. And a laser is a collimated beam of energy. It's a coherent, highly coherent beam. And so as it travels through this gradient, it scatters at each part. Light scatters at each part of the gradient, creating basically an image point for us to see all along the path. And so this is not at all how images work. An image is incoherent, diffuse light scattered from the object. This is a collimated beam of energy. And so the coherency was what allows us to see this. What I always say is turn off the laser and tell me and show me that you're bending the image of the laser pointer around an obstruction, not the laser itself, because it's a misattributing an effect of refraction with lasers and construing that with image formation. So, and I think coherency is the reason why we can see this laser throughout the gradient, and it's again not analogous to image formation of objects. So I just wanted to touch on lasers briefly. The last thing I wanted to get into here to kind of tie this all together is geometric optics. And so this is a book by Euclid called Euclidis Optica, and I believe it's the oldest recorded any type of information or on geometric optics. He's the grandfather of geometric optics as far as recorded documentation. And this guy in his book, he had this quote I really liked that kind of summed it all up for me. right in the intro of his book, and I want to read this quote and kind of break it down real quick, and then we'll just get into some optics. But so he says, let it be assumed that lines drawn directly from the eye pass through the space of great extent. So we can, basically he's saying, we can draw our line of sight with lines. We could represent them with lines. And that the form of the space included with our vision of cone, with its apex in the eye and its base at the limits of our vision. So we can draw a geometric cone from the optical system and we can represent it with lines, and we can, and this is a geometric relationship our vision has with reality. And then thirdly, he says, and let those things upon which the vision fall are seen, and that those things upon which the vision does not fall are seen. So he's basically saying within that cone of vision, things that are in that are things that can be seen, and things outside of that cone of vision cannot be seen. And so
what a fantastic citation.
Yeah, and this guy, I mean, these are the fundamentals of geometric optics, the way I see it and the way I've been understanding it, and the way it's drawn in diagrams and expressed. And so geometric optics, it ultimately comes down to the eyeball, and we're replicating the perfect system that our eyeball is, the amazing system that it is. And so what I really just wanted to highlight here was the important parts of the eye when we're talking about geometric optics is like the pupil, which is what lets in light. And we have the outer lens, the cornea, which refracts the light into the pupil. And the iris controls the pupil. And then I didn't know this, but we have a secondary lens in the back of our eye. And not only do we have a secondary lens, but this lens can flex and it moves. So it's like it's a morphing lens that helps us focus amazingly well. And I was looking at geometric ray optics diagrams, and I was, they're always using spherical surfaces and multi-lens setups in the diagrams, and I was kind of like wondering why. And it's like, oh, they're replicating the eye. The eye is the system that geometric optics is fundamentally trying to, or this is where it all comes from, is the eye, basically. So I wanted to highlight a few things here. The important parts of the optical system that we're going to be talking about. We have the sensor, which is like the retina. This is where the image is formed in our eye on the sensor. We have the lens, which is that like the cornea of our eye. And then the aperture would be the pupil. And this is our field of view. So we have based on the relationship of these things, we have a geometric relationship with reality and what we can see. And so we'll keep going and just talk about, so this is just a nice little diagram showing that cone of vision that Euclid was talking about. And based on the mechanics of our eye, we have a specific cone. And here is like the most basic optical system. This is a pinhole camera diagram. So all you have is a hole in a box that's letting in light. And so that's the aperture. This is the sensor. This is like analogous to the retina, and this is the image. So this is where geometric optics comes in, and it starts to describe all these points. And there's a geometric relationship between what we see and what's in reality. And this is what geometric optics is describing, and these principles that they've found. And so this is a diagram of the pinhole camera. We have basically the object plane, the field of view here. Rough diagram again. This is that where the aperture is letting in the light, and this is the sensor. And so this is a quote. Well, I want to talk about object space, which is going to be the left side of this diagram here, or the candle. This is the field of view which defines object space. And that's important. It's going to be important moving forward. I want to give this quote. This is from, I believe, Born and the Principles of Optics by Born and Wolf. And what they say here is, in an ideal optical instrument, every point P in the field of view is of a three-dimensional region called the object space. This will give rise to a stigmatic image. The totality of the image point defines the image space. The corresponding points in the two spaces are said to be conjugate points. So that's all I want to highlight there, is that the points in our geometrical field of view are the object space, and they have conjugate, meaning connected points within image space. So there is a connection between those 2 points within this geometric system. That's what makes them conjugate. And so this diagram just kind of highlights that. We have O, which is commonly represented for the object. In object space, the light is described as rays here. It's entering the optical system and then coming back in our eye, forming the image on the retina here. So there's a link between object space geometrically and image space. This is another diagram kind of showing the conjugacy of object space and image space. So going further with that, there's a principle in geometric optics called the principle of reversibility. So where should I say? These rays further, by the principle of reversibility, if I is the object point, each ray will reverse its direction but maintain its path through the optical system, and O will be the corresponding image point. The points O and I are said to be conjugate points for the optical system. So the principle of reversibility states that you can swap the object point with the image point, reverse the light, and it will be mappable within your geometric field of view. That is a requirement for image formation, is this principle of reversibility. So they describe the light as coming in. I'll use this diagram. Here's an object. They describe the light in rays as coming into the optical system, hitting the sensor, the retina, and this is mappable back to, you can measure all the refractive indices, however many there are, and it has to be mappable back within object space, which is determined by the field of view. So no matter how much refraction is going on, the reversibility states it's reversible to object space, an object point within the field of view. This diagram kind of might help a little bit. It shows the eye up top here, and it's looking at an object submerged in the water. We have two different, we have the air and the water here. And so the light is going to travel and bend, and this is going to be reversible back down to the object point. If you can measure the refractive index, you can reverse the light rays back to the object point. So in conclusion, kind of went over a lot there, but I want to just bring it home by saying I postulate that image formation requires a couple things, and it's not just light bending. One, light from the object must reach the observer. So the object, even if it is in our field of view, the light does need to reach our eye, and that's as far as the initial claim goes. They say light bends, therefore it bends around the ball, therefore we can see it. But no, it's not just about light bending. Image formation is not just about light bending. It's about light from the object must be mappable to the optical system's geometric field of view. And again, we're talking about the image of within it, like the Chicago city skyline, within our geometric field of view, it must be mappable. So yeah, I think that's about all I wanted to say on that. I hope some of that was clear at the end. I know I kind of breezed by it, but yeah, I think that's everything.
No, you did a great job, man.
Yeah, cool, man.
you tie together a lot of key concepts, especially regarding the geometric optics with the principle of reversibility. I mean, that just goes so in tandem with how you were saying that it's a line of sight phenomenon for the refraction, for what we see to even begin with to hit our eye. But if you like, and then going back to one of the first images that you show was the sun setting behind the building, and the building, casting its shadow. Well, the shadow is created by an object blocking the light rays. So, like that would, like, if the Earth curvature
Right.
was, lowering that building, it would be, what was it, 200 feet above instead of like pretty much the whole building. So it's like we have these
Yeah.
nice crisp shadows that just couldn't exist if they weren't line of sight being blocked directly to us, because the light coming to us from them is what's being blocked, not light that isn't hitting our eye at all. That's insane. So
Yeah, I mean, yeah, a shadow can't block the light of the sun. That's why I call it like a mini Canigou observation. With the sun was right behind the silhouette of the mountains. It's like so the city skyline's getting refracted up and then blocking. So refracted light is blocking refracted light. Like, what's happening? That's what the claim is, basically.
That's illegal. Can't do that. Non-converging light rays don't block anything.
Yep.
Yo, have you seen Life is Short, a concept for vision, Vamby?
Dude, and Vamby, do you know why it won't block anything? Sorry, Shane, but it would interfere with the principle of reversibility. You wouldn't be able to geometrically trace it back to its source. It converges to nothing, or to a place
Bingo.
where light doesn't converge. So yeah, it's like this simple fundamental principles. Just, you can't. You have to make a special pleading for this in all
Exactly.
in all observations, for you're just like, oh, it just so happens that in this case, refracted light blocks it. It blocks light, dude. All right.
Yep. It's all just assumed.
Yeah, have you seen Life is Short on YouTube, Vamby?
It sounds kind of familiar, but I don't think so.
The one that I usually
Maybe.
cite him for is Angular Resolution in Our World, where he does some stuff. But the one I'm speaking of now is a concept for vision. It's like a 2-hour prez on optics, and it starts with trying to represent what we see in a linear world with our spherical eyes. So you have, the juxtaposition of the spherical, as you were denoting with the picture of the eye, and optics and rays. That's how it starts, and then it goes into vanishing point, angular resolution a little bit, but mostly it does a fantastic way of describing, I think, what you're talking about, but it does it only at one boundary interface. So what it's showing is exactly like bottom up, regular obstruction, linear compression. It shows the specific math on how, you can represent it parabolically, spherically, and linearly under 100 miles as what you started with. And I think it would be a good supporting thing for what you were showing. If you haven't seen it, you should check it out.
Yeah, I will. I actually remembered now. I think you linked that to me like way back, and it was like so dense I couldn't even bite into it. But I'm getting a little bit more acquainted, so I probably can handle it now.
All right, here I'm going to skip to one of the ends, and it says things disappearing with distance, and how you can describe things with standard terrestrial refraction as it's misinterpreted across warm surfaces as 7/6R, or more commonly 14% less than the curvature of Earth. Am I striking a fancy? Am I seeing with the parallel for what you were going through? Yep. It's exactly.
It's all reversible. Yeah.
Yep.
But yeah, geometric optics is quite a lot to chew on. And I remember when I first started looking at it, like the diagrams didn't even make sense to me, or it's like I'm so not used to looking at these types of things. But once I understood, they're mimicking the eye. And so it's like, oh, now I get why it's all coming together. It's all mimicking the eye. It's all based on the optics of the eyeball.
And then they reverse engineered it. Instead of saying, hey, we see things spherically or whatever with our eyeballs and we're trying to observe a linear world. They go, actually, you know what it is? We see forever in perfect lines, but the ground around you is curving at exactly the same rate as it would infinitely from the rate at which you can't see it anymore. It's just curving down perpetually. You're like, oh, that would look the same. And that's the whole trick.
Just ignoring perspective and how how images are formed and how it's all mapped in our brain is perspective. Yeah.
And they go to represent it. They do a side profile orthographically with, you know, disappearing horizon where there is no horizon, and they go, boom, this is how, you know, why you should see China if the Earth were flat.
Yep. Yep. I'm still waiting for someone to show me, you know, actual in the lab proof of refraction coming around and bending around an obstacle or obstruction within a single medium. Like that's what I'm searching for.
You already provided their best evidence, which was that picture of that laser light in the tank with the salt medium. That's what they show all the time. And they go, what? You don't think laser lights can bend? Boom, infinite refraction, no matter what you say. Like that's the entire argument. And that's all the evidence I've ever seen is that exact picture of that exact laser light bending at the density medium on the bottom. So
yep.
He also showed the second most bestest one or whatever, which is the non-analogous, adding another medium to cause the boundary interface for the image to be lifted up on. So it was the one by putting the mirror in front of the house, or not mirror, but the lens in front of the house, and then the lads in the lab or whatever with the or no, I'm sorry, not that one. It was the propane one when they had to shoot propane or release propane gas next to a thing to get it refracted up.
Yep.
Well, excellent presentation, dude. I think you did a really good job. I think you went through it really well.
How's the audience looking? Got any questions or comments to field out there?
Looking good. I was just taking a Gandy over there. Everyone is basically saying Bambi did a fantastic job presenting. They absorbed all the information, and they can't wait to tell all their friends about refraction and boundary interfaces.
Yeah, some immediately credited your presentation to Alan and I for picking you out, so that was cool. So we got some adjacent credit for your
nice.
Or whatever. Yeah, that was cool.
Yeah, it's hard for even me to grasp the stuff. Most people can't. You hear the word refraction, and that's too much. And you say the word, say geometric optics, and it's it's white noise. But it's interesting
geometry.
Yeah, it's really interesting when you start to slowly understand it, or get a better understanding. Yeah.
Perspective is one of those things that's like wonderfully complex and it makes so much sense, but the simple lie is so much easier to spread. And that's how we got in this kind of position that we're in today. Where it's
instead of explaining how you see things, what if, hear me out, we're just standing on it?
It's so much easier to buy and like easier to understand. Simple lie or the complex truth, right?
Now, this is where the Globies open up a second can of copium. And they hit you again, everything since Canigo, and this one you're showing right now, where they say, okay, are you looking at the object or are you looking at the shadow? And after it doesn't matter what your answer is, they go into the convolution of, well, okay, now do shadows refract too, buddy? Like seriously? And they pretend again that they've somehow won the argument. It's amazing to watch.
Unlucky. All right, lads. Well, I think we can wrap up here if that's all we got for this week.
Thanks, guys.
Yeah, that was awesome.
All right, we will be back next week. I don't know what will be presented, but probably Shane will be presenting something on the history of measuring the distance to celestial bodies in the mainstream paradigm. So we're talking radio wave measurements of moon bouncing, Venus bouncing, and I think we're going to dabble in the sun.
So it's another Cabal puppet show. That's what you're saying.
Yes.
Can't wait. Can't wait.
Going to do a review on Cabal magic.
We're going to look at how people bastardized Kepler into thinking that it has physical meaning into real units, probably, right? There you go. Like we really know the ratios of the everywhere, but we don't really know how far it is. But we can say we know how far it is because we know the ratios.
Extremely important concepts to understand and dismantle, because based on how we see in this geometric cone of vision that we may or may not have, the distances for everything that are derived are just based off of a periodicity of when they'll return. So it doesn't necessarily have to have the same kind of physical meaning that you would think it does. All right. So we'll be back next week for that. And then Monday night, if you guys are following the Space Audits YouTube channel, we'll be doing Celestial Theodolite update number 26. Tune into that. That'll be a huge one. We just did the biggest update to the spreadsheet since its inception, and we'll be going over all of that with some new air bars, new graphs, new things to discuss. So that'll be Monday, 8 p.m. Eastern. We'll be live on my channel, and then Tuesday, Shane will be doing that presentation on the measuring of the old celestial bodies, probably. And then we'll be back Friday for Twitter community night. See what the lads are doing on Twitter.
Nice.